Hello, everyone. Welcome to discussion 2. In this discussion, we're going to be going over more linear algebra, some more probability. We'll also be doing some matrix multiplication problems, and lastly, we'll be doing some like machine learning term categorization problems. So it's going to be a lot of fun. And so for problem 1, it's the linear algebra question, by the way. Here are some quick things that you should be familiar with before we start the problem. And so first of all, what is the spectral theorem? Well, given that we have some matrix A that is an n times n square matrix of real numbers, here you can see it in math notation, and here's like this lovely little square matrix, we know that A is symmetric if and only if A is orthogonally diagonalizable. That word is actually so hard. And so what does orthogonally diagonalizable actually mean? Well, here we have a more clear definition, hopefully. And so some matrix A is symmetric, which is also orthogonally diagonalizable, given that it consists of real numbers, if it's the case that we can decompose A into this matrix multiplication, Q, D, Q transpose, where Q, I can't actually use this. Okay, Q is some orthogonal matrix, and D is some diagonal matrix. Now, before getting into the details, what do they all mean? Recall from, I guess, linear algebra / pre-calculus / multivariable a little bit maybe. Orthogonal means that two vectors or more vectors, they're kind of like, you can think of them as being at 90 degrees. An orthonormal vector, those are vectors that are not only orthogonal, but also have a magnitude of 1. And lastly, what is a basis? Well, when you have like some number of vectors that create basis vectors, basically all these vectors are linear independent, and when you have some kind of linear combination of these vectors, they span the entire space. In this case, you can see that this vector 1 and vector 2 over here, any linear combination of these two vectors span the entire R2 space, or like the 2D space. Yes, 2D space. And so, given those terms, now let's go back. So Q is some orthogonal matrix. What orthogonal matrix actually means, it's kind of an annoying term. It means that this matrix has an orthonormal basis. Specifically, in this case, where A is symmetric and orthogonally diagonalizable, it consists of an orthonormal basis of eigenvectors. Recall that an eigenvector is a vector that satisfies this formula here, AV equals lambda V. And so this is going to be very helpful later. And so this is what Q is, some orthogonal matrix that consists of an orthonormal basis of eigenvectors. Then what is D? Well, D is a diagonal matrix, and this diagonal matrix consists of the eigenvalues corresponding to those eigenvectors. Okay, and so that's the spectral theorem. And so number 2, some quick review. This you might actually have seen in pre-calc. I think I might have been like trolling for the previous question. But for two orthonormal vectors, v1 and v2, recall that when you take v1 transpose times itself, this is, you can think of it as like you're multiplying every element with the vertical version of itself, right? Because it's like transpose times itself. And so it's equivalent to like v1 dot product itself. And recall this equation. If you don't remember, it's fine. But basically, v1 dot product v1 is equivalent to, oh no, my iPad died. Okay, we're back. v1 dot product v1 is equivalent to the magnitude of v1 times the magnitude of v1 times cosine of theta, where theta is the angle between the two vectors we're dot producting by, in this case 0 degrees because they're the same vector. And so the magnitude of v1 is 1 because we're talking about orthonormal vectors, and the magnitude of v1 is also 1, and then cosine of 0 degrees is 1, and so v1 dot product v1 is equivalent to 1. And this is going to be very helpful later on. And so alternatively, if you're multiplying v1 transpose by some other orthonormal vector, v2, that's not itself, that's equivalent to the dot product, we have the same equation here, except now it's v2 instead of v1. And remember, orthonormal vectors have an angle of 90 degrees between them. And so cosine of 90 degrees is 0. And so we have 1 times 1 times 0, which is 0. Okay, and so that's number 2, what you should recall. And lastly, number 3, you'll see it in the problem, so it's fine if you don't exactly remember it now. But what does positive semi-definite mean? Basically, some symmetric matrix is positive semi-definite if for all x vectors, which are of dimension n, we have x transpose times some matrix A times x is greater than or equal to 0. And remember, we have some symmetric matrix A. Okay, and so that's all you need to know for question 1. So let's dive right in. So we have a symmetric matrix A, which is of dimension n times n. And it says, we're defining what positive semi-definite is here. So this matrix is positive semi-definite if for all x of dimension n, we have x transpose t, or xt, ax is greater than or equal to 0, so what we just talked about. And what we want to show is that A is positive semi-definite if and only if all eigenvalues of A are non-negative. Okay, and so because we see if and only if, we know we have to prove 2 ways. And so we can start by proving the first way, which is basically saying, given that we know that A is I'm going to just write, A is symmetric, which we'll see it's important, asymmetric, and we want to prove that A is positive semi-definite. So this is true if, or sorry, let me rephrase that. So if this left part is true, then this right part is true. And the right part is all eigenvalues of A are non-negative. Okay, and so how do we start that? Well, first we should probably kind of get an idea of what do we know about A, right? So what do we know about the left side that can help us determine the right side? Well, because A is symmetric, we know that A is also orthogonally diagonalizable. And so we can say that what we know is asymmetric, which implies that A is orthogonally diagonalizable. And we also know that A is positive semi-definite, right? We can assume this is true. And so the definition of positive semi-definite is right over here. And so we can just literally copy past that. So for all x vectors, we have x transpose times A times x is greater than or equal to 0. Okay, and so given this left information, we need to show this right information. And so how do we do that? Well, let us see. So we can start off with some equation that we have here, right? We know that x transpose A x is greater than or equal to 0 because that's given to us as part of what a positive semi-definite matrix is. And recall that A over here, A can be, or sorry, not A, x can be any vector. If x can be any vector, this means it can also be an eigenvector. And so this we can say that V transpose A, V is greater than or equal to 0. And since A is, or V is some eigenvector and there could be many eigenvectors, or there probably should be many eigenvectors, if n is greater than 1, then we will just have a subscript I over there. Okay, and so remember what an eigenvector actually is. an eigenvector satisfies AV equals lambda V. Recall we had that over here if you forgot. And so notice how we very conveniently have an AVI right over there. And so we can replace this entire thing by VI transpose times lambda VI is greater than or equal to 0. And recall that lambda is what? It's just a scalar. Yay! So if it's a scalar, we can move it to the front. And so what we have over here is lambda VI transpose VI is greater than or equal to 0. And recall in our notes, when we have some vector, this is not just a vector, by the way, it's an eigenvector that we got from our orthogonal matrix here, which consisted of an orthonormal basis. And so remember, when we have this as the case, we can use this first rule where we're essentially taking the dot product of ourself. And so this entire equation is just equal to 1. And so what we have is lambda times 1 is greater than or equal to 0. Therefore, lambda is greater than or equal to 0. And this lambda should also have a subscript, by the way, just because every eigenvector has its corresponding eigenvalue. Sorry, I forgot that. And so we have just proved part A, which is that given that A is a positive semi-definite matrix, all the eigenvalues of A are non-negative, and you can see that by right over here. Perfect. And so now we have to prove the opposite. And the opposite is slightly more complicated, but with the tools that we got from from our notes, it shouldn't be too bad. Okay, let me just add one more page. And so for part 2, what we're trying to prove is, given we know that the eigenvalues of A are non-negative, we want to show that A is positive semi-definite. And so given that the eigenvalues of A are non-negative, aka given that lambda of I is greater than or equal to 0, we want to show that A is positive semi-definite, aka this particular equation holds true. Okay, and so when eigenvalues of A are non-negative, what do we know? Well, we don't know that much, but I guess for this case, what's actually helpful is we try to kind of start from the right side and go to the left side. But because we did that mathematically, we can also start from this true statement on the left side and then go to the right side. So like the work I'm going to show, once we flip it over, creates the proof. But yeah, to be easier, I'm first going to write down some things we know. So as a reminder, if we know matrix A is symmetric, right? That's given in the problem right over here. A is a symmetric matrix. And so again, we know that A has this nice property where A is equal to some orthonormal matrix times some diagonalizable or diagonal matrix consisting of eigenvalues times Q transpose. And again, on the left side, we know that the eigenvalues are all greater than or equal to 0. And so let's actually start by using a little bit of what we know from Q. And so let's let the eigenvectors of Q be represented by some set of V, where we have V1, V2, V3, ... all the way to Vn. And recall that these form an orthonormal basis, right? So this is an orthogonal matrix that is created by an orthonormal basis of a bunch of eigenvectors. What does that mean? So remember, an orthonormal basis means that we can create any vector by writing it as a linear combination of these vectors. And so because of that, we know this following statement is true. If we want to create some random vector x, well, we can write it as a linear combination of all of our eigenvectors here from Q that form an orthonormal basis, because we know that A is symmetric. Okay, and it's symmetric and it consists of all real numbers. So A1, V1, so we're just writing this as a linear combination of, and that should not be a plus sign, of all of these eigenvectors, dot, 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 A and Vn. And with some gorgeous mathematical notation, we can write this as the summation from I equals 1 all the way to n of AI times VI. Okay, and so we want to show that this is true. And we have some equation for x being equal to this guy. And so now I'm going to do the little backwards thing where we want to try to create xtax, right? But we can't really show anything about this. What we can show, what we do know is that this is true. And so I'm going to replace the x with, like, the x is over here with this definition that we created here. And so doing that, I will get summation of I equals 1 to n of, so some linear combination that creates this vector x transpose times A, and then some other linear combination, I'll tell that j. We have AJ, VJ. I have a friend named VJ who was on course staff. That's funny. Okay. AJ, and then we have VJ, and that's not a transpose. Okay. And then we can set that equal to, what I'm going to do is I'm going to take this transpose and I'm going to move it inside over here. And yeah, I'll just do that for now. And then so we have, this is equivalent to summation of I equals 1 to n of AI. And remember, A is just a scalar, right? A linear combination is like scalar times vector plus scalar times vector plus scalar times vector. And so the transpose doesn't really apply to a scalar. So we have this. Oops. We multiply it by A, and then we multiply it by this. Gorgeous. Okay, and so here is a subtle part about summations or double summations that is good to know. Because these parts are scalars, we can like take the scalars out, kind of. And so think of it, I'm gonna bring like the summation out, I equals 1 to n, and I'm gonna take this scalar out, and then I'm gonna bring this summation here, and I'm also gonna take this scalar out. And then everything else, like, obviously just because I take the scalars out, that doesn't mean that the i's and j's don't apply. They still do, for sure. And so I still have the VIT, and then I still have the A, and I still have the VJ. And the reason we could do this is because, again, these are scalars. Okay, and so this is equivalent to, okay, if you guys notice here, again, yay, we have this lovely AVJ. And so what does that remind us of? That reminds us of this formula. And we do know that V is an eigenvector, right? That's how we define V. And so what we can do is we can replace this with lambda J V J. Okay. And so writing this out again, we can also just reorder the summations. It doesn't change anything. I'm just going to move this summation like over so it looks nicer. This is equivalent to summation I equals 1 to n, j equals 1 to n of AI, AJ, and then we have VI transpose. And then here's where we replace the AVJ to lambda J VJ. And if anyone's ever confused about double summations, just think of it as you're just summing every element of a matrix, where AI, AJ is like AI times AJ is some like one element of the matrix, and we're iterating through I and iterating through J, like a double for loop, basically. Okay, Now we're going to continue by moving this lambda j outside. And so that will get us something along the lines of I equals 1 and j equals 1 n of ai times aj times lambda j times vi transpose vj. And so this is where the interesting part is. This is also where the notes that we talked about earlier is very helpful. And so notice what this looks like, right? This looks like vti times vj, which is like the dot product of two vectors. And remember, I can go from 1 to n, j can go from 1 to n. And so as a note aside, we have two cases here. We can either have I equal to 1, or sorry, I equal to j, or we can have I not equal to j. And so if I is equal to j, what happens? Or actually, you know what? It's fine. Okay, so if I is equal to j, then we have dot product vit of vi, which is basically dot producting ourselves. And so this is like saying that we're doing vi times vj, which is equal to vi times vi, which is just equal to 1. What about when I is not equal to j? Then we're doing vi dot product. There's a dot product here, by the way. Vi dot product vj, which is equal to, well, dot producting two eigenvectors, which are orthonormal, which they're 90 degrees, which equals 0. And so given that we have this case 1 and case 2, now we can see over here that we're either going to run into case 1 and case 2. Anytime that I is not equal to j, well, this is going to be 0. So this entire thing is going to be 0. So it doesn't actually contribute to the sum. So the only time we actually contribute to this summation is when I is equivalent to j. And notice that when I is equivalent to j, do we need these two summations right over here? Not really, right? Because if you think about like ai aj as like every like element in a matrix that you're like looping over twice, anytime that I is not equal to j, it's going to be 0. And so we're only going to be ending up summing up the values that are along this diagonal where I is equal to j. And so we don't really have to like for loop twice, if that makes sense. Like we can just like advance I once, but like for every like one for loop, we can do like ai times ai, ai times ai, ai times ai, and that like covers it all. So if you think about it as like one for loop is sufficient because we only care about the cases where I is equal to j and the dot product is 1 and actually contributes a value, we can rewrite this as the summation from I equals 1 to n of ai times ai, where j has been now turned to an I because they're literally the same over here, which is equivalent to, you can just write it as ai squared. We still have the lambda j, and then we have vi transpose vj. Okay, and so we also mentioned right here that what happens when we do have, oh, I'm sorry, why did I write why I write vj? This should be vi. But like when we're dot producting the same vector, well, this is just 1, right? And so we end up with the summation of I equals 1 to n of ai squared of lambda j times 1, which is just lambda j. And notice, what do we know, right? We are given that all our eigenvalues are non-negative, and we want to prove that a is positive semidefinite. So we want to prove that this equation is true. Well, since this is greater than or equal to 0, and ai squared has to be greater than or equal to 0, right? It's literally a square. This actually, yeah, has to be greater than or equal to 0. Then you know for a fact that this entire thing must be greater than or equal to 0. And so we've just shown the spectral theory, or not the spectral theory, that this matrix A is positive semi-definite, because we've just shown this, right? We start out with XTA of X, and we showed that this is greater than or equal to 0. And so even though we showed that this was true, we didn't assume that this was true, right? So it's kind of like we started on the right side, but like we weren't going backwards, I guess, because we used only the truth from the left side that we knew. And we thus showed that this equation is equivalent to that. And so therefore we have just proved the converse of our previous statement. So we've proved number 1, we've proven number 2, therefore we have proved the entire statement right over here, and that concludes problem 1. If you forgot all your linear algebra and want to review on spectral theory, I did quickly put a little link right here that I wrote. Sorry if my handwriting is unreadable, but it's web.uvic.ca/tilde=c/math110/sec lowercase dash spectral.html. It goes over the spectral theory for matrices with real numbers, and it's really good to help you refresh with exactly what is happening right over here. Okay, I'll see you guys in the next problem.